here Professor Jackie Baek, who is an assistant professor at NYU Stern in the Department of Technology, Operations, and Statistics, and this is a bit of a homecoming back to Simon. She was previously a fellow here, and it was data-driven decisions a couple of years back. And yes, please.
All right, thanks so much for the introduction. Very happy to be here, and thanks to all the organizers for organizing this amazing workshop. So I'll be presenting this work, which is joint work with Ali Maktoumi, who's at Duke. And at a TLDR of how this work kind of fits into the theme of the workshop is that we should sometimes be thinking about kind of long-term outcomes, because long-term outcomes can often be different than short-term outcomes due to potential feedback loops. And so sometimes we may want to try to model the feedback loops to try to have an impact kind of more in the long term. Let me see if this works. OK, great. So all right, so let me start with the motivation, which is OK. I'm sure everyone here knows that algorithms are very prevalent and used for many different high-stakes decisions. But there's many examples of deployed algorithms exhibiting some sort of undesirable biases. Here are some famous examples of, I'm sure many of you are familiar with these examples. So for example, like Amazon was using some algorithm to try to help with recruiting, but the recruiting tool kind of gave an explicit negative score to women, and then they had to scrap the tool. And there's kind of similar examples in other applications like criminal justice and healthcare that I won't go into. So that we're like, OK, maybe how would we fix these problems? And so there's obviously been a lot of work from many people also, in this workshop as well. So one approach to kind of addressing these kind of issues has been from the perspective of kind of algorithmic fairness. So there's been a lot of work kind of in this from this research community. So one way one approach that has been proposed is kind of let's impose kind of fairness for these algorithms. So there's lots of different fairness notions that I won't get into, like imposing some sort of constraint like demographic parity. OK. OK, so this was kind of just one approach, but I would say, but kind of one critique about this kind of approach of kind of imposing fairness is does it actually help, right? Does it actually, do the thing, improve the system, improve it in a way that's meaningful? And one way in which these imposing a definition does not help is that the way that these are defined is often in a static setting. It's kind of a one-shot prediction problem, and let's impose some constraint. But as I mentioned before, this doesn't necessarily account for long-term impact. So if we're thinking about, does something help in the long term, then we can't really even ask these questions in a static model. Okay, so this kind of motivates the idea that maybe we need to study the dynamics of what's happening, and maybe in some situations we do want to model some sort of dynamics. And so this is the high-level motivation of what we study. Okay, so in our work, we're going to focus on a particular application, which is hiring or school admissions. Basically you can think about a firm that's hiring applicants over time. And we're going to model, motivated by this, we're going to model some dynamics. Okay, and of course, dynamics are kind of hard to model. It's hard to predict what's going to happen 10 years from now because of this particular intervention. But we're just going to focus on a particular set of dynamics, which I think is somewhat first order in this application, which is that a firm is better at evaluating applicants from groups it has hired from in the recent past. Okay, so this will induce some dynamics that I will formalize mathematically in the next couple slides. But we're just going to model this set of dynamics, and then we're going to kind of analyze this dynamics and see what happens. And we're building upon a literature called Statistical Discrimination. This is a literature from kind of economics from the 70s, and we're going to build on a classical model of Phelps. But mainly, this is a static model, and the main novelty of our work is that we're going to try to model these dynamics. Okay, so I'm going to start with describing this model of Phelps from the literature, and then we'll extend it to this model that has dynamics. So, okay, so let's start with this Phelps model. Okay, so here, each applicant has a scalar skill S that's drawn IID from a known prior, normal 0, 1. And the applicants are associated with, let's say there's only 2 groups for simplicity, A and B. And basically higher skilled applicants are better, right? Like firms prefer people with higher skill. But the firm does not get to observe the skill exactly, right? So they get to observe O, which is S plus epsilon. And right, so there's some noise term, right? And this noise term is mean 0, but the variance is going to be a function of the group, right? So for some groups, there's like just more noise, right? Because the firm is not as good as evaluating these applicants. Okay. But based on this, we're in a Bayesian setting. So the firm uses this observation to update their belief about their true skill given the observation. And because we're in this like nice model, a firm's inferred skill about an applicant is just you take the observation and you divide it by 1 plus this standard deviation of or variance of the noise. That's just the formula. So what does this mean? It means like, let's say now there's 2 groups. The groups, their true skill is drawn from the same, their true skill distribution is the same across A and B. But if you look at the distribution of the inferred skill by the firm, it's actually going to be different because the variance of the noise is different. Okay. And so if the firm is making decisions based on this quantity, then you'll get differences in outcomes, like let's say hiring outcomes, between the 2 groups, just because of this, this noise term being different, right? Even though their underlying skill distribution is the same. Okay, so this is the Phelps model, and it's isolating the fact that okay, no, it's not like explicit discrimination, it's called statistical discrimination, like differences between groups arise because of differences in this noise. Okay, so we're going to, any questions on this base model? We're going to expand it into a dynamic setting.
Is that generic? It's just going to be some threshold on skill, and then so you're just going to take the effort.
Yeah, that's what we're going to assume actually. I'll say that in the next slide. Yeah. Okay, so here we're going to introduce a dynamic model where now this noise is going to have a little t term, right? And this is going to change over time, and I'll tell you how this changes. Okay, so here, like you can think about groups as like just as a running example, like new grads from college, 2 different colleges. Like I'm like Google interviewing people at from these different colleges, and t can be years. Just so you have some example. So our model, like you can actually, you just consider one firm making hiring decisions for one group of applicants. Okay, so let's just consider like one college. Okay, so here's the model. Okay, so just some notation. P is the kind of group size. It's like the mass of applicants. Okay, and the hiring rule, as Emma said, the firm hires all applicants whose inferred skill is greater than a threshold tau. This is an exogenously given parameter. Okay, everyone above a particular scale, I'm willing to hire them. Okay, so the process starts off at some initial state, which is the initial noise variance at time t equals 1, and QT is the percentage of applicants that are hired at time t according to this hiring rule. Okay, and then the main modeling assumption, which is the dynamics, is that the noise variance updates. The noise variance at the next time step is a function h of p times q. P times q is just how, you can think of it as how many people were hired at time t, right? Because q is the percentage, p is the total mass. And then h is a decreasing function, which means that if more people were hired, then in the next time step, the noise is smaller, right? So I hired more people at time t, in the next time step, the amount of noise for that group is smaller, right? So that's the main modeling assumption we're we're imposing, and like this is modeling the idea that a firm is better at evaluating applicants from groups it has hired from in the recent past. Right? So like, why would this be? Well, a firm can learn about the skill of their past hires through their performance as an employee after you hire them. Maybe they train a machine learning model, so the noise kind of decreases as you have more samples. Or maybe current employees, the people you hire will be part of the recruiting process in the next year, and they're better at evaluating people who came from the same school as them. Right? So, but both of these things are one thing is that we only consider things updating like in the next time step. So your noise is only a function of the number of people you hired in the previous time step, but not like all past time steps. Because basically, we're saying that like things that happened 20 years ago, like you're not going to be using data from 20 years ago to like train your model now. So we're saying that only things happening in the recent past impacts your noise in the current time step. And for simplicity, we're just saying it's only a function of the previous time step, although the results hold with like any like finite number of time steps. Yeah, question?
So technically sigma t plus 1 could be bigger than sigma t, right?
Yeah, exactly. Yeah. So, okay, going back to the model, for this talk, we'll assume that h has this function of 1 over x. This is kind of like if you think about x as the number of samples, right? So we're modeling kind of how variance decays as the number of samples grows larger. But most of our results hold for like different functional forms of h of x. Okay, so let me just illustrate one step of the model so that everyone's on the same page. The model, the state is just defined as the noise at time t, which is sigma t. That induces some distribution of this inferred skill, which is this. There's an exogenous threshold, so then you hire everyone above this threshold. That's this shaded region is qt, which is the percentage of people that are hired. And then I plug this qt into my h function, which I assume is like 1 over x, and that gives you the noise variance at time t plus 1. And then you just repeat this process to see what happens over time. And yeah, like this number might be greater than or less than this number. Okay, and so we'll denote by the function f, the function that maps the noise at time t to the noise at time t plus 1, basically going through this process. So we just have to understand what f of x looks like to understand the dynamics of this process. Okay, and in particular, what is important is whether f of x is greater than x or not. Okay, that's the most important thing. Is the noise increasing over time or is it decreasing over time? Right? So we mainly want to understand how f of x looks like compared to x, right? So if it's greater than x, it means the noise variance is larger at the next time step, right? And vice versa. And if f of x is equal to x, that's actually a steady state. Okay. Okay, so just to give an example, here's a function, here's a drawing of what f of x might look like. And I've also drawn y equals x. That's the dotted line. Okay, so if f of x looks like this function, then this actually, you can actually understand exactly the dynamics of the process. Okay, so there's basically a couple regimes, or there's actually only two regimes. Okay, so the first regime is, let's say your initial noise variance starts in this region. If you're in this region, f of x is always higher than x, right? So this means that your noise will increase over time. Right, so let's say you start at 4, the next time your noise is 5, and then at 5, the next time your noise is 8, and so on. So here, your noise eventually will diverge to infinity if you start in this region. If you start in this region, f of x is less than x, then your noise actually keeps decreasing over time, and you actually end up converging to this point. And then if you start here, you're above x, and it increases over time, and you actually end up converging to here again. So if your initial noise starts in this region, you actually end up converging to this point. Does that make sense?
The right-hand side seems weird, right? That would just say like you get more and more and more uncertain over time, and that seems like a strange model. So I just,
Yeah, like it does rely on the modeling assumption that like your data is not necessary. Like let's say we're training a machine learning model, but like we're kind of saying like we're assuming that we are only using the last year's time step to train your model. So you're not. It's not like your data is always getting bigger. So that is a modeling assumption. Yeah. But yeah, like even if you're only using the past 10 time steps, this would still happen. Yeah.
If I'm understanding correctly, currently we can basically analyze one group at a time because you're taking everyone above the threshold.
Yeah, great. Yeah.
How would this change if there's like a capacity constraint? And
Yeah, great. Yeah. So this is another kind of big modeling assumption about this basic model is that there's no competition among groups because we have this exogenous threshold. So yeah, we have an extension in the paper where we have a capacity constraint and then we take, so two groups are competing and we take, so then we end up getting similar results, but it's not as like kind of clean as this. I don't remember if I have it in a later slide, but like the main insights still hold under that model. Yeah.
And I'm following up on one of the questions earlier. So if you basically update sigma t plus 1 based on not only how much you observe, which is the PQT, but also sigma t. So you kind of like a Bayesian update type thing, right? So you don't move that much from sigma t. Then, I mean, this is kind of an open-ended question, but would you still fall in that range?
Yeah, actually, we analyzed that model in the paper that like sigma t sigma t plus 1 can't jump too much further from sigma t. Yeah, that's actually the model we have in the paper, and we would still get this kind of this particular kind of pattern. Yeah. So yeah, this is kind of the main. Okay, so here, basically, there's only two outcomes that can happen, right? Yeah.
Thank you.
Yes.
So is there something about the model that makes sure that f is a monotone function or a unimodal function or something like that? Or, I mean, could f be arbitrarily complex compared to what you've drawn here?
Oops. I think f is, I mean, okay, our result is that f looks like this under our modeling assumptions, but I think f being, monotone is just saying, oh, when there's less noise, you can hire more people because you're more certain about what they're, I think f being monotone would occur under most reasonable modeling assumptions.
Is that something you could prove, maybe, that f is monotone under your modeling assumption?
Yeah, I mean, well, f is monotone under our modeling assumptions, under our particular modeling assumptions, but of course you can try, you could ask oh, how general is this result under slight relaxations, and I think that's a pretty benign thing to show, yeah. Okay, so basically there's only two outcomes that occur. That's the noise going to infinity. And the thing is that when noise goes to infinity, you actually, in the limit, you end up hiring nobody because basically your signal is useless. And then you estimate everyone to have 0 skill eventually. And assuming your tau is greater than 0, you end up hiring nobody. Whereas if you started here and you go to this steady state, you end up hiring a positive number of people at every time step. Okay, so this is kind of the good steady state, and this is kind of the bad steady state. Okay, so that's kind of the main, that's the kind of, the first main result of the paper is that under our modeling assumptions, f has this particular shape and therefore has these two steady states. Or there's a regime where there's only one steady state, which is bad, but that's not I guess that's not as interesting. It's the interesting regime is that when there's kind of two distinct steady states. Okay, and so why is this interesting? Well, what is the implication is that now let's think back to having two groups. Okay, so again, this result was just for one group, but the same curve. Let's say we have two groups and they're the same size, then the same curve holds for both groups. But basically, what happens to each group is just a function of their initial condition. Okay, so if it happens to be that their initial condition, which is the noise, for group B was their noise ended up on this side of the threshold, and group A, their noise was on this side of the threshold, and this was 20 years ago. Over time, the noise, if you run the dynamics, the noise is going to, kind of disperse over time, and you can see that eventually group B will not, no one from group B will be hired because they'll be in the bad steady state, and then group A will converge to the good steady state. Yeah.
But in this case, the proportions of both have to sum to 1, right? Because if you have to hire either from group A.
Oh, sorry. Here we're not in the model where the groups are competing. Like both groups are running this model kind of independently. So I'm just saying, where the groups end up. It could be different depending on the initial condition. Yeah. So, right, so here, the main implication is that it's kind of giving one explanation for why kind of historical disadvantages can persist and exacerbate over time because of this kind of feedback loop, right? Even though the groups are identical in their kind of true skill distribution. Okay. Okay, so I'll just kind of briefly talk about the literature. Like again, like this, we're building on the literature on statistical discrimination. There's this kind of like seminal model of Phelps, and we've just kind of directly extend the model by adding this dynamic generalization. There's also kind of another group of work called, there's another kind of seminal model called the arrow model, which is a more game theoretic model. And they actually show that in a game theoretic model, there might be multiple equilibrium, like Nash equilibrium. And we're kind of saying something similar, like we're saying like, oh, there's multiple steady states, which is kind of, not exactly the same because we don't have a game, but like it's a kind of a similar spirit to multiple equilibria. So we have like a similar type of result, but like the underlying kind of mechanics is a bit different. Okay, so now now getting into like interventions, right? So now let's say we have some group that's kind of in a bad position. This is like, let's say a disadvantaged group, right? So then, how would we like help this group, right? So I'm not gonna get into like particular interventions. Like examples could be like, oh, maybe we should just like hire more applicants from this group, or we should spend more time during the interview, we should like spend more time evaluating them, right? But like if you look at this picture, what we need to do is we need to reduce their noise, right? And specifically, we actually want to reduce their noise so that their noise is reduced beyond this threshold. Okay, so basically, if I categorize interventions into kind of a mild intervention that reduces the noise but only by a bit, versus a more quote unquote drastic intervention that pushes the noise further out, right? So essentially, the green one intervention is like way better than this purple intervention because once the group, the noise is below the threshold, then the group will actually naturally head into the good state. Whereas if you just do a mild intervention, okay, sure, in the short term you did reduce their noise and maybe you hired more people, but once you lift the intervention, then the group will just go back to this like bad state. Okay, so this is saying that like, basically, drastic interventions, even if they're only short term, drastic interventions can be more effective than mild interventions. Even if a mild intervention, you can hold it, you can do this intervention for a long time. As soon as you lift the intervention, then you'll kind of go back to the bad state. So relating this to kind of real world examples, we can think about the recent Supreme Court case where they kind of banned this affirmative action at US colleges. Like one way to interpret this, you can think about affirmative action as an intervention that was in place for a long time, right? And then they recently lifted this intervention. So this is very recent, but some preliminary data says that actually like black enrollment has declined at many colleges since the lift. So one way to interpret this under our model is that maybe the affirmative action was kind of a mild intervention, and once you lift the intervention, you're kind of going back to a bad state. Of course, I'm not claiming that our simple model is explaining the complexities of the real world, but like this is kind of one, perhaps like one mechanism that's happening in this application. So okay, so I just have like a couple more, maybe 2 more points. So here. the model like also formalizes the idea that smaller groups are worse off, because smaller groups, like their function will look different in a systematic way, and the systematic way being that the threshold to converge to the good state is smaller, which is worse, because like it's harder for the smaller group B is smaller, to converge to the worst state. So it kind of just like formalizes the idea that smaller groups are worse off. Okay, lastly, this is going to be my last point. Like, we just do some numerical simulations that try to confirm our qualitative findings of this model. So, obviously we're studying a pretty stylized model that has, all these modeling assumptions and like, but so here we simulate a system that's kind of more replicates a real world setting where here each applicant has some feature vector that's drawn, and like their true skill is like a linear function of their feature vector. And like in every period, the firm is just trying to estimate this beta coefficient just using like linear regression. So we kind of like simulate, at each time we draw some number of applicants, we draw x's from some like normal distribution, and the firm like uses linear regression to estimate this beta, and then they use this estimates to like hire some number of people. So it's kind of like more, it doesn't really make the same assumptions of our like stylized model. But basically, we're trying to understand how the system looks like as a function of the initial conditions. And the initial conditions is just like you start out with a particular data set of size n, right? So if you start with a large data set, it means you start with a pretty good understanding of beta, okay? And basically, we show that as the size of the initial data set increases, then the eventual percentage of people you hired after 100 time steps, there's like a stark threshold where if there's kind of like, if your initial data set is too small, then you end up hiring nobody from the group because your estimates become worse and worse. And again, here we're assuming that you only use data from the previous time step to like estimate beta. So we get the same qualitative result that there's like a threshold in which like if your initial conditions is worse, then you end up at the bad state where you end up nobody being hired at time 100, and that after a particular threshold, then you actually converge to this particular hiring rate of like 22% after 100 time steps. Okay, all right, so that's it for, so here just a summary, and yeah, happy to take questions either now or later. Thanks.
We have time for one or two questions here, and then we'll get our next speaker set. Yeah,
So, from the firm's perspective, does it matter in your model, right? Like if everyone has the same distribution of skill, why do they care? Like, from their perspective, why do they care about group A versus group B? Like, they're not.
Yeah, like their hiring rule, they don't care, but they might want to like, they might want to impose some kind of intervention if, because like if the group is in a better state, then in the future you'll be able to evaluate them better and get more good candidates.
And I'm bad at B, and I just always hire A, but they all have the same background distribution. It doesn't matter for my firm in the end, right? Like,
yeah, but it would be better if you can evaluate both groups better, so that there's like a larger pool than you can hire from in the future. So you might be able to get better candidates.
The expected skill of my candidates would be the same, right? Like even if I never hired from group B and only A, because they have the same.
No, but yeah, but you're trying to pick out the best people. Like, or if you're only good at picking out people from group A, you're kind of losing out on half the population because like, oh, like I want to hire the best people, right? Yeah, if you're hiring people at random, yeah, obviously it doesn't matter which group, but like.
But if they have the same distribution, the top 20% from group A is equal to.
No, but it's hard to pick out the top 20% because of the noise. Like, if the noise is infinity, there is no top 20% because you estimate everyone at 0. Like,
okay. I think I'm maybe confused about the two-group case then, because if I don't hire anyone from group B and I only hire people from group A, eventually I know group A really well.
yeah.
And then I get the top 20% correctly from group A and miss out on everyone from group B. But the top 20% from group A is equivalent to the top 20%.
Yeah, but it would be better if I got top 10% from group A and the top 10% from group B. Then my expected skill would be even better than having top 20% from group A.
But I thought in your hiring model, you just select anybody above the threshold.
Yeah, so in the model, yeah, but I guess I thought the question was kind of like, oh, why should firms care about this? And maybe they would increase their threshold eventually, right? If they.
I see. I think the question is maybe a little bit about how is that captured in the model, and I think this is an interesting tension here about. I think.
Yeah.
Yeah.
No, that's a good question.
I think your instinct is. I think I understand your instinct.
Okay.
Here, but
Yeah.
I think one of the questions was how is that shown?
Okay, we don't show that in the model, but yeah, we do have an extension in the paper where we do have competition across the two groups that I didn't show.
I see. Yeah, I think maybe that was a.
Okay,
that was a little bit
sorry, yeah.
A little bit of ships crossing there. Okay, let's do one more question while we get our next speaker set up. Yes, Tina.
Yeah, so I'm wondering if you've thought about, because you talked about these like more drastic, more mild interventions. I'm wondering if you've thought about dynamic interventions in this context, because it sounds like, drastic interventions can be very costly.
Yeah.
But it sounds like, to push the state towards like this kind of desirable regime, you can implement a more drastic intervention at the beginning, and then you can make it more mild over time because you're kind of closer to that kind of boundary where things behave well. So yeah, have you thought about kind of the dynamic intervention?
Yeah, that's a really good question. I haven't thought about it. Or we haven't tried to model this, but I think that is the intuition of interventions being of different horizons. I think is kind of one of the main points that drastic intervention is costly, but maybe it's not as costly because you only have to have it for a short period of time compared to a mild intervention that you have to have for 20 years. So but we haven't tried to model exactly what's the optimal interventions. That's a good point. Yeah.
Well, let's thank our speaker one more time. Fantastic. Well, next up we have another regular here at Simons, which is I always see you here at Berkeley. So.
Yeah.